Let's take a look at forces and angles. I have here a cart which has a mass of, whatever it says up here, 3 kilograms, which I've labeled M sub C for mass of cart. And it is on a ramp attached to a spring scale. So this is a spring scale. You may have seen them before. Basically, something just hangs on it and it shows the weight. In this case, the weight is in newtons. And that's what we're going to be looking for. We want to know what is the reading on this spring scale with this cart. So the first thing I'm going to do is I'm going to define a plane, or pardon me, a set of coordinates, a set of axes, and I'm going to define this direction to be x and this direction to be y. Okay? So normally horizontal is x, right, and vertical is y, but I'm just going to redefine everything and say that x is parallel to the surface of my ramp and y is perpendicular to the surface of my ramp. Right here I've got a few different forces. I have my force of the weight of the cart that's pushing down. I have the force of the tension on the cart caused by the string, and I have the normal force, which is at right angles to the surface of the ramp here. If I were to draw a free body diagram, I would draw it exactly like that. Okay, so I have my force of tension, I have my force normal, and I have my force of weight or force of gravity, like that, with this one here and this one here being at right angles to each other. On a free body diagram, we have a single dot, and all of the arrows come out from the single dot, and they are all real forces. No components. We don't split it into x and y. We don't write down net force or any of that sort of stuff. A free body diagram needs to have only real forces, all coming from a single dot, and they all point away from the dot. But now on our picture, we are free to add all kind of other stuff. So what I'm going to do is I'm going to come in and I'm going to look at this as if this was a right triangle. So I've got a perpendicular direction like this, and I have a parallel direction like this. So now this right here is the part of the weight that is pushing in towards the ramp, the opposite of the force normal. Okay? So this is the weight part pushing in towards the ramp, and this angle right here, by virtue of rearranging and opposite angles and all that kind of stuff, this angle theta is going to always be this angle theta. Okay, so this angle right here is the same as this angle here. So I want to define what these two arrows are, these two components. All right, now I'm never going to draw components on a free body diagram, but I can draw them on my picture all I want. So this one right here, since it's the adjacent leg of this triangle, I know that this component, this force of weight here, it's going to be the cosine of the angle times that force of weight. And it's going to be, that's also opposite to the force normal. So I'm going to call that my normal force. So I'm just going to say my normal force is equal to my force of weight times the cosine of 30 degrees. And then I'm going to go one better, and I'm going to change my force of weight. What is the force of weight? The force of weight is mass of the cart times gravity, isn't it? Mass times gravity. So I'm just going to replace that. I'm going to say that right there is mg. Okay? So my normal force is mg cosine theta. That's the force pushing down this way, so that's also the force pushing up that way. This one theoretically is negative, right, because we got g. And then, of course, that one would be positive. That's the object pushing up. So what about this? What is it? The force going down parallel. If I look at my definition of my axes, that's clearly in the x direction. Okay, going down that way in the x direction. So I'm just going to call it F sub x, and it's going to be equal to mg, which is my force of weight, times the sine of 30 degrees. mg sine 30. And if I do my substitution in there, which we can do, let's go on and plug in these numbers. So my f of x is equal to m times g, massive cart, mc g, times sine of 30 degrees. So it tells me my cart is 3 kilograms. For g, I'm going to use minus 10 meters per second squared. And the sine of 30 degrees is 0.5. So I end up with 3 times negative 10, which is 30, times 1/2, is equal to negative 15. And that's newtons. So that's the force down the hill. So what is the force of tension that holds it in equilibrium? Yes, positive 15. So my force of tension must be equal to the opposite of that. So it must be equal to 15 newtons. Okay? If it's in equilibrium, it must be. Now, if the cart was still moving down and it was like stretching or something, then it would be less because the cart would be accelerating down. But there we go. The cosine stuff for the force normal, that is a question on the test, so that's why I threw that in there too. One way to remember that it's the sine that's pointing down, and I've mentioned this several times already. Remember, sine slides. Sine slides. So the sine, when we talk about gravity pulling down, the component of gravity that is in the direction of down the ramp is the sine of the angle times the component of gravity. So that's our F sub x. And, of course, the length of that arrow should be equal to the length of the tension force. And really should be, I should look at the normal force and the gravity force and figure out, we could do that with a complete the parallelogram. If all my drawing was actually to scale, we could do this. I can't do that very well. Anyway, it would be something like that. My artistic skills aren't that great. But anyway, this would be the force of x, which would mean that would also have to be the force of tension. But they would balance each other out. All right, everybody got that? Copy down? Next one's going to be a little more difficult. Now what I've got is a cart in a similar situation, but it is not attached to a spring scale, nor does it need to be in equilibrium. It is attached to a string which goes over a pulley which connects to a hanging mass. And so I've designated that M sub h. So we have M of C, which is the cart, and M sub h, which is the hanging mass. So let's take a look at how we would solve this. So I'm going to define again my xy coordinate system over here so that x is in the uphill direction and y is perpendicular to the plane. So this is my normal force here. And then I'll have gravity pulling down and tension pulling up in the x direction. So my free body diagram is going to look identical to the previous free body diagram. We're going to have gravity going this way. We're going to have the tension force going this way. And we're going to have our normal force going this way. I say it looks identical. It'll be off a little bit because since this isn't necessarily in equilibrium and may be moving, there may be a net force. That's one of the things we're going to talk about here in the question. So I'm going to make the assumption that it's going up. It's accelerating up because this mass is, first of all, heavier. And if it was on a pulley and I had a heavy thing and a light thing, the light thing would go up and the heavy thing would go down, right? So this is heavy, plus there's even less force necessary because this is on an incline. That's why we use wheelchair ramps, right? Because it's easier than lifting straight up, going up a ramp, right? So even if these were the same mass, this would come down and this would slide up the incline. And since this is heavier, for sure, this is going up, which means this tension force, F sub t, is actually going to be greater than the component of gravity pointing down. But we need to figure out how much that stuff actually is first. So I have my force of gravity, which is equal to the mass of the cart times g. I have these two, so I have my, let me do this in a different color. So I have my Fx and my Fy. The Fy is equal to mass of cart times g times the cosine of 30 degrees. And my Fx, I know that looks like a y, like an x, doesn't it? And my Fx is equal to mass of cart times g times the sine of 30 degrees now my force normal is just going to be equal to this, the opposite of this, right? So the Fy, that's the force down in the y direction, so the force normal is in the up direction, and it's going to be identical to this in magnitude. This right here, the force of x in the x direction, that's the force wanting it to go down the hill, right? That's the force that makes it want to go down the hill. But tension, the force of tension, makes it want to go up the hill. Everybody see that? So I've defined x in the positive direction to be up the hill, haven't I? X is up the hill. So tension is going to be positive. It's going to be going up. So I'm going to look at this right here, and I'm going to say, what are all the forces that are acting on this? So the sum of the forces on the cart in the x direction are equal to the tension, right? The tension. And then what's acting in the opposite direction? Gravity, right? Which is x, the F sub x. So the tension minus the mass of the cart times g times the sine of, well, I don't have to put theta, I'll put 30 degrees because we said it was 30. So these are all the forces that are acting on the cart. There are two more, right? We said there's the component of the weight that's in this direction and the component of the normal force in that direction, but those are in the y direction, aren't they? Those are in the y direction. And I'm only looking at the x direction, which is up and down the hill. So now, let's take a look at the hanging mass. The hanging mass, I have the force of weight here, Fw, which is equal to the mass of the hanging mass, m sub h times g. And then I have tension. And tension on this one is pointed up, isn't it? It's pointed up. Now, let me ask you a question. Is the arrow that I draw for tension greater than, equal to, or less than in size from gravity? Less. You said less. Why?
It's going to fall down.
Right. If it's accelerating down, then that means the tension is not enough to hold it up, right? So my arrow, and there's sticklers about this on the AP exam. You don't just draw a dot and put some arrows on it. They're going to look and they're going to say, can it be noticeably seen that this is smaller than this? They'll look at that. Okay? So this is my force of tension, F sub T, or just T. I need to stick with one thing or the other since I put T there. And then this is my force of weight on the way down. And let's do something else. Let's also define a coordinate system or a set of axes here. So I'm going to define this to be my y direction and this to be my x direction. Why do you suppose I did that? Right. I defined this to be x over here, but now that I'm over here, let's define this to be x, and then this to be y. What forces are acting in the y direction? None. Right. It's just hanging there. And the forces in the y direction over here are balanced by the normal force, so there's no y's over there either. So it's real convenient to represent this as x. So let's look at the forces for the sum of the forces that are acting on the hanging mass. That's going to be equal to, well, this is force that's going down, right? So that's going to be my mass of my hanging mass times gravity. And then what is tension doing? Tension is acting in the opposite direction, negative x, right? It's negative direction on this direction that I set up. So I have my force of gravity minus the tension. That's the sum of the forces acting on this. Now, would you agree that if I treat this as a whole system, because it's tied to it, it's tied to stuff, right? They're tied to, the two things are tied. Like I can't, if I lift one, the other goes down, and if I lift this one, it goes down, right? They're attached to each other. So, so my net force is going to be on this system. The net force is going to be equal to the sum of the forces on the two parts of it, right? So my net force on the system is going to be equal to T minus M sub C G sine theta, sine 30 degrees, pardon me, let's fill in the number, plus M sub H times G minus T. What do you notice? T cancels. Yeah, T cancels in this case. Since I'm not interested in what T is anyway, because I could solve for it if I knew some other stuff, but I'm not interested in what it is anyway, and I'm looking at the net force of the whole system, so what's going on inside the system doesn't matter. So I'm just going to rearrange this and say that this is MHG minus MCG times the sine of 30 degrees. Okay? Since this is a minus, I don't like starting with a minus. Let's start with a plus and then put the minus in there. And this makes sense too, because I can see if this is going down, making this slide up, the net force is going to be equal to the weight of this thing going down minus the weight of this thing pulling back the other way, right? So there it is, and that's exactly what it is. So now let's substitute in the numbers. So we have the cart with the mass of 5 grams, or 5 kilograms, that's this over here. So 5 kilograms times, and I'm going to plug in 10 for G, 10 for gravity. And if I plug in minus, we can rearrange all this. But let's see, meters per second squared, and then times 0.5. And then over here, the hanging mass was 6 kilograms. So 6 kilograms times 10 meters per second squared. So what I end up with is 60 newtons minus 5 times 10 is 50 times 0.5 is 25 newtons. And then that's going to be equal to 35 newtons. And if I really want to worry about the gravity, minus 10, stuff like that, what I really have to do is I have to think about why did I use 10. And I use 10 because, rather than minus 10, because when we have things like projectiles that we learned about before, the difference between going up and going down matters, right? So we defined up to be positive and down to be negative. But look at the coordinate system that I defined like this. What is going in this direction on this x-coordinate? Is that positive or negative? If I have a normal x, y, as I go this direction, am I going positive or negative? Positive, right. So when I define my x-coordinate system to be this direction is x, right? Then as I go this direction, am I going positive or negative? Positive. So that's why I use plus 10 for gravity. Because gravity is pulling in the positive direction here, isn't it? Yeah. So when I defined this, my tension is positive, but my gravity is negative. That's why I'm subtracting this. Okay? Because really, I have to do a little bit of a logical thing in my head, because really, I can sum these. I could say the sum of these is this plus this, right? Because it is. It's tension plus gravity, but gravity in this case over here is negative, right? So this is negative 10, or I can just say 10 and put the negative right here, right? I know it's a little confusing. The best thing to do is to think about which direction is something pulling, and is that positive or negative based on the coordinate system, the set of axes that you defined. Okay? If it's pulling in the positive x direction, then that's positive. And if it's pulling against it, then it's negative. Okay? Okay, so this is one of your questions on your test. Everybody confident they can do this? All right? It all boils down to this. It really does. It all boils down to this. I just derived this. Okay, last one. Makes me wonder why I erase this sometimes, because so much of this is the same. But I'll leave that there. The length of the arrows might change to protect the unknowns. But anyway, this question says a cart with a mass of 6 kilograms is placed on a ramp with an angle of 30 degrees. The string goes over the top to a hanging mass, and the system is in equilibrium. The system is in equilibrium. So what's the mass of the hanging mass? So one of the things that we did was we calculated like the net force and all that, which we could do all of that. We could calculate forces over here and divide by G to get, we get the forces in newtons and divide by G to get the mass. But there's actually an easier way to do that. So we know that the force going this direction is equal to the mass of the cart times G times the sine of 30 degrees, right? So mass of the cart times G times the sine of 30 degrees. And this is going, I guess we could say it's going in the negative x direction. Okay. This over here is going in the positive x direction. It's pulling the other way, right? And we know that if this system is in equilibrium, what do we know about a tug of war with one pulling one way and one pulling the other way? They have to be equal, right? Okay, they have to be equal. So the magnitude of this number, negative or positive, has got to be equal to the negative. It's got to be equal to the magnitude of this number. Okay, and the magnitude of this number is the mass of the hanger times G. Do we have anything in common? Yeah. Got gravity in common. So let's get rid of that. We could make a ratio out of these if we wanted to. We don't need to. Let's just go on and plug in the values. What was the mass of the cart? I can't find it. 6 kilograms. There it is. I should put those in bold. So 6 kilograms. And the sine of 30 degrees is 0.5. That's why I pick it all the time. Is equal to the mass of the hanger. 6 times 0.5 is 3 kilograms. Is equal to the mass of the hanger. So we need half as much weight on the hanger to keep this from sliding up or down when the angle is 30 degrees. Okay, that's why I picked that 0.5. If we moved it up to 60 degrees, then this would be 0.866 or 45 degrees or whatever. So there's different, obviously, sines and cosines, but I pick ones I can do in my head. You won't be so lucky. You'll need a calculator because Canvas is just set to pick random, random angles. I think, the angle will be somewhere between 20 and 50 or something. I don't remember what it's set for. But it'll pick random angles. But this is a question on the test. So we've now done 4, if you count the calculating the normal, right? I think one of them I just calculate what is this, right? Remember sine slides? What is the force? If I cut the string, what's the force making it want to roll down the table? That's it right there, right? And then I have one where I have some friction. I say the force of friction is equal to some random number, 2 newtons. What's the net force down the hill? Which means you just calculate this and subtract that. And then you've got the force. Okay? Everybody think they can do that? All right. So you've got 2 videos to watch as well. One of them is a guy who actually has a little cart on a ramp, and he does have a little spring scale, and he's doing the actual measurements, with the weight in the cart and the normal force. And then at one point he drops the ramp away because he's replacing the normal force with a string. That's right towards the end of the video. Kind of neat. So watch that, take notes. The other is an experimental design question, which I've told you is always on the final or on the AP exam. So work that one the way they tell you to. I expect to see it in your notes. Then you'll take a picture of your notes and upload that. So the 2 videos plus this. Well, you don't need this. You took notes on this paper. But at least the 2 videos in addition, I want to see those notes, especially the experimental design. Okay, that's what I'm going to be checking to see if I can read it and that you did the experimental design stuff the way they asked you to. And then take your test. By all means, take it multiple times. Take it 10 times, or take it once and get a 60 out of 60. I don't care. But it's a test, and it's the biggest test we've had so far, and it's probably the easiest test we've had so far. Okay, so.